A kind introduction. You've already heard me talk for 90 minutes, so you'll have to stand me for one more hour. My talk today is titled Information Theoretic Perspectives on Learning Algorithms. This is very different from my previous talk. This is joint work with Adrian, who is my student in math, Ankit, who is jointly advised with Polling. He's in the CS department at Madison. Okay. So this talk is going to be about is related to learning theory, of course, but it's the main, I guess, point of this talk is to give a different perspective on how to think about learning algorithms. In particular, how one might use information theoretic ideas to gain some insight into how these optimization algorithms or learning algorithms work. Okay. Feel free to stop me anytime. This is a very large auditorium, so it might seem daunting to like raise a hand. But it's fine. I mean, it's the same people, just a bigger room. So yeah, feel free to stop me. Okay, so I'm going to start with the quintessential kind of a learning algorithm or learning problem, which means that you have a bunch of points xi, yi, and you want to fit a curve. Okay, you in this case I've plotted points in R2, and I want to fit a curve which seems to describe the relationship between these xi's and yi's in a nice way. Okay, so I'm going to refer to this problem as a forward problem. So I have a data set which is a bunch of points, and I want to reach a curve. So you can think of a curve as also as a function of r to the d for some d, because you can parameterize a curve. Say it's a polynomial of a certain degree, so you can always parameterize this curve using its coefficients. So I'll think of a curve as basically some point in some r to the d space. Okay, so here are two ways one might fit a curve. Okay, so on the left hand side I have drawn like a quadratic looking curve which seems to roughly go through the points, and on the right hand side I have this really wiggly curve that is trying really hard to fit all the points. Okay. Intuitively we feel like the left seems to be correct, so no math here right now. It just feels like the left is a fit, whereas the right is an overfit. It's trying way too hard to go through all the points. Right, that's just our intuition. We feel that way possibly because the one on the right is just too wiggly. Okay, the too wiggly is clearly not a mathematically correct term to describe what is wrong with the curve, but you could try and describe it using some other concrete language, saying that it's not very stable, which means that if your x-axis happen to change a little bit, the y point that is predicted changes by a lot. So you could say something like it has a very high Lipschitz constant, or it is very high derivatives, or you can characterize this wiggliness of this function or the stability of the function using some other language as well. Okay, but the intuition is the same, that on the right you have a very wiggly curve which seems wrong, and on the left you have a nice looking quadratic curve that seems to fit the points. Okay, so I'm going to now focus on a different problem, which is the reverse problem, guessing the points from the curve. Okay, so let me draw the picture. On the left, I now give you the curve. This is a quadratic, and our job is to figure out where were those endpoints such that they generated this particular quadratic curve when I use some algorithm to fit them. Okay, so this backward problem, which is trying to go from the curve to the data set, seems to be really hard here, because well, we know, or even if we know the algorithm that generated this curve, we know that the points are somewhere around this curve, but we don't know exactly where they were. We know that they were somewhere around it and they seem to follow that quadratic pattern. So it's kind of a hard problem to solve here. But if you look at this picture, it seems to me that it's much easier to solve it here, because the only reason the curve must have gone here is because it was trying to fit a point. Then it went from here all the way here. Why? Because it was trying to fit some other point there. Okay. So if you look at this wiggly curve on the right, the overfitted curve, the problem of guessing the points from the curve is suddenly much easier than in the non-wiggly kind of a curve. And just the intuition here is that the overfitted curve is somehow containing more information about the data set than the regular kind of nice quadratic kind of curve. So the more information here is where information theory can enter into the picture. So you can ask this question, well, it contains more information, but in what sense? Can you quantify this information and quantify the information content to say how wiggly it is or how much it is overfitting to your data. Okay, so that's kind of the content of this talk. So I'm going to first explore the connection between information and overfitting. This was first observed by Shu and Roginski in 2017. I'll then go into a class of algorithms that you can analyze using this connection between information and what is called generalization error. And then I'll explain why sometimes using information theory is not the best way to get bounds, because sometimes you get bounds which are not useful, you get bounds which are, say, infinity. And one way to get around that is to just not use information theory but use some other kinds of tools. So I'll explain how to get some bounds using optimal transport, ideas from optimal transport theory, and then I'll just conclude and throw out some open problems. Yes?
What is the motivation for the backward problem?
Right now there is no motivation. It's just an observation that the backward problem is easier when your curve is overfitting. So if there is a way to quantify this connection, that solving the backward problem is related to how much you're overfitting. So that's just the, so right now I'm not saying that the backward problem is important to solve. I'm just saying, well, if for some reason you are interested in solving it, it would be easier if it were overfitted. Yeah. Okay. Okay. So in information theory we have channels. So you have some X and that goes into a channel and a noisy version of X comes out. So in order to even try to use some information theoretic ideas, we try to fit some kind of a channel model here to try to see if you can analyze these learning algorithms using information theoretic channels. So one way to model the original problem is as follows. You have a box. The box is the channel or the algorithm. The input to this algorithm is what the data that you observe. So in this case, let's say you're observing n IID samples, x1, x2, xn, that are coming from some distribution. Okay, so let's say you're observing these points xi, yi coming from some distribution, and your output is now going to be the curve. Okay, so input is a bunch of points, output is a curve. So as I said again, the curve can be thought of as just a vector of coefficients of describing that curve. And your algorithm is this transformation. So the algorithm takes in points and outputs a curve. Okay, so in information theory, what you generally have is the channel is not in your hands, like the channel is nature. What you can do is to play around with the input, try to code information in a clever enough way so that it becomes immune to whatever the channel does to it. But here the difference is, well, the channel is entirely up to you. You get to decide how the transformation from S to W is happening. Okay, so in that sense, it's very different from channel coding. It's related to some other concepts in information theory that I'll touch upon at the end. But I just want to say that the difference is S, the data set or the input to the algorithm is not in your hands, that's just nature. But you can do anything you want in that box, the channel box, which is the algorithm, and produce that S. Okay, so I'll pause here and say, why do we need a channel? So this channel is essentially a transformation. So it's a PW given S. So what is the probability of getting a certain W if my data set is some S? So you might think that this channel is complicating things unnecessarily, because really, why not just have a deterministic function? Right? You have an F, you have some function which looks at your input data set and gives the parameters. For example, if you're doing regression, you have a closed form expression for the slope of the line that is the least squares kind of fit. So why do you need some randomization here in the middle, the algorithm, which is giving you a distribution over a set of all possible lines? Well, one way to think about it is, this is kind of a Bayesian perspective on the problem, that you have these, you're kind of taking an average over all possible things that can happen. So whenever we are in the analysis, we are also going to optimize over the randomness in the data set as well. Another interpretation is, we really are interested in the randomized algorithms. Yes, least squares does give you a closed form expression, but really if you're using something like stochastic gradient descent, the curve that you end up outputting is not going to be the same every time you run the algorithm. It's going to be something different. Right? So what you really are getting is some kind of a distribution on the output space. So that's why it does make sense to think of the algorithm as some kind of a randomized transformation from from the S space to your W space. Okay. All right. So I said that designing the algorithm is akin to designing this channel. But what is the purpose of designing this channel? Well, the purpose is to minimize some loss function. So there is some loss function that we get to decide. And our job is to design a channel or design a PW given S, that probability distribution, that is minimizing a loss function that is defined over your W cross X space. Okay. So the best choice of W from a Bayesian perspective is choose a W that is minimizing your expected loss. Okay, so this expectation is taken over the true distribution mu, and you're calculating the loss of a particular W over the true distribution. And what you'd like to really output is the best possible W. So the best possible W is that W which is minimizing the expected loss over your data set in expectation, right? And this is what you would like to output, but of course you can't really solve this problem, right? Because you don't know the true distribution mu. All you have is a data set, right? So for example, all you have is images of cats and dogs, some 1 million images of cats and dogs, but you don't know the true distribution that is generating these images of cats and dogs. So all you have is your data set, you don't know mu. So you try to do the next best thing. So instead of looking at the expected loss over the true distribution, you look at the loss over the empirical distribution. Okay, so this is the empirical loss, so you just evaluate the loss at the points that you have seen, because that's the best you can do. And then you try to output a W that is going to try and minimize this loss. Right? Okay, so just to clarify, so this problem may be hard because the loss function, this minimizing the empirical loss could be like a non-convex kind of a problem, and it may be hard to solve. So we kind of just hope for the best. We write down the empirical loss, say that I want to minimize this, and hope that the W that I get from here is close to the actual minimizer of this loss, and it's also close to W star. Okay, so that's the general idea of this, considering the empirical loss. Okay, so now I want to introduce this term generalization error, which was kind of new to me when I first encountered this, and it was a little bit confusing. So it's probably useful to spend some time on this particular slide. Okay, so really, so what I have written here is the expected loss. So the expected loss is kind of the test error. So if I give you an algorithm which is generating a W looking at your data set S, then the loss that this particular algorithm is going to give me is the expected loss over X and W. So I'm taking the expectation over everything, the expectation over the random data set S and the expectation over the randomness in the algorithm itself, so S and W. So this is a joint expectation over everything that is going on in my model, the data generation and the output of the algorithm. And that is something that, this is the test error, and that's what we want to minimize. So that's what we care about. The second slide is saying that this is the training error, which is the expected empirical loss. Okay, so here, okay, so this is the test error, which means that, so forget what I just said. So what this is doing is you're first calculating a W using your data set S. So you look at your data set S and you generate a W. Now you take that W and you test it on a sample that it hasn't seen before, right? So that's what you define by test error. So this X here is actually completely independent of your S and W and everything else. You have a data set S, you generate a W, take that W and you test it on an X that it hasn't seen and calculate the loss that you get. And that's your test error. Okay, so the key thing to note here is that this X is independent of this W and also of the S, the data set S. The training error is what I accidentally said earlier. The training error is when you're taking a joint expectation over your W and S. Okay, so you look at your S, you generate a W, and you calculate the loss over the joint distribution. So here the W, the output, is dependent on your S, and you're calculating the loss on the same S that was used to generate that W. Okay, so that's the difference between these two, that here the expectation is taken with respect to the joint distribution, And here there's actually some independence going on because the stuff that you haven't seen is independent of the stuff that you have seen. Okay, is that sort of clear? Yeah. All right, so this is the test error, this is the train error. We don't really care about the training error. What we really care about is the test error. The test error is small, then everything is fine. Okay, okay, so now the third term that I'm going to describe is the generalization error. So this is the expected loss, which is the same as the test error. So you can write the test error as this is just an identity, expected test error minus train error plus train error. Nothing new happening here. Turns out that this particular term that I've written here, test error minus train error, is what people refer to as the generalization error of an algorithm. Okay, so I'll just pause and try to explain why one would write an expected loss into these two components. Again, we really only care about this term, but if you want to analyze this term and say that this expected loss is small, for analysis purposes it's sometimes better to break it up into these two parts. Okay, so this training error depends on the optimization algorithm that you are using to find in the empirical risk minimization, right? So this is just a function of kind of the optimization algorithm in the that is minimizing your training loss. The test error minus train error, it's somehow trying to figure out how well is your algorithm performing between the data set that it was used to train it and some data set that was completely independent of what it was used to train on. And you can intuitively understand why this is the generalization error. So for example, if this quantity is really, say, if the test error is really high, so if this quantity is really big, then it means that the test error is large but the training error is small, which means you probably overfit to your training set, right? So you drove down the training error but your test error is very high. So the difference between the test error and train error is some metric of how well your algorithm is performing on these two sets. And you ideally want your algorithm to perform roughly the same on both the same. You don't want it to perform really well on the train set and really poorly on the test set, because that would be an indication of overfitting. Okay. So that's why we call this the generalization error. It's trying to capture how well your algorithm is generalizing to unseen data. Okay, so this generalization error, I've now essentially just written it as the difference between this first term and the second term, but I made a little bit of a change that here the expectation is now taken over the product distribution PS cross PW. It will take you a moment to figure out, but this is exactly the same as this. All I've done is instead of taking one single sample X, I've taken n independent samples X1, X2, Xn and taken the average over that. The expectation remains the same because for each sample X, the expected error is this particular quantity. I'm just adding those errors, dividing by n, and getting the same value. So there's nothing super clever going on here. Just rewriting this first quantity as an average over n independent unseen samples.
Sorry, the first quantity is S given or is are there many samples of S which are average over?
Right. Okay. So in the first inequality, so S is given. Using that S, you generate a W, and using that W, you test it on an unseen set, let's say S bar. And S bar has the same distribution as S, but S bar is independent of S and W because it's unseen. So if it helps, you can think of this as S bar. So it's that unseen set, but since it has the same distribution, I'm continuing to call it S.
But the first thing is conditioned on S.
The first thing is conditioned on S, but if you look at the LWX, there is no S showing up. So we only care about the marginal of W. So we don't really care how that W is obtained. It only depends on the marginal of that W. Yeah. Yes?
Generalization error and test error are synonymously used. So is there any special purpose of defining generalization error as the difference of test error to train error?
So generalization error is synonymously used as test error because train error can be driven down to zero, or at least I believe that is what is happening in modern machine learning algorithms. The training error is anyway zero. So if you want to calculate generalization error, you might have, if this term is zero, then you have an equality. And if you look at how, say, people use deep learning algorithms for training, you'll never see someone not driving the training error to 0. You always make training error 0 and then ask what is the test error, in which case you might as well refer to those two as the same thing. But really they are different. Yeah, if you were to stop at some earlier point where training error has not yet gone down to 0, then they would be different. Yeah. Okay. So if you look at this expression on the bottom slide, you have some expectation of a function. It's just that once you're taking an expectation over the product distribution, and the second time you're taking an expectation over a joint distribution. Now, if you have if you have taken an information theory course, you would recognize that these kinds of terms show up in information theory quite often. In particular, they show up in the definition of mutual information itself. Okay, so I'll maybe just do a quick one slide introduction to all the tools of information theory that I would need for this talk. So the first is just mutual information. So mutual information is a way of quantifying how much information X contains about Y, or how much information Y contains about X. Okay, so one way to define mutual information, it's the KL divergence between the joint distribution and the product distribution. Okay, that looks similar to here. So there is something, this is some notion of separation between the product and the joint, and this is also a joint and some notion of separation between the product and the joint. And mutual information satisfies two nice properties that I'll need in this talk. The first is what is called a data processing inequality. So data processing inequality just says that if you have some original random variable X, it gets corrupted into Y, that Y gets corrupted into Z, then the mutual information between X and Y is bound to be larger than that between X and Z, because Z has had two corruptions along the way, whereas Y has only had one corruption. So that's what the data processing inequality says. And the second is there is mutual information satisfies what is called the chain rule. So if you want to calculate how much information Y contains about two things, X1 and X2, you can calculate the information Y contains about X1, and then conditioned on that X1 how much extra information is remaining that Y contains about X2. Okay, so of course you can flip X1 and X2 around and get the same equality with the signs, with the indices exchanged. But really these are the only two inequalities, only two properties of mutual information that I'm going to need: data processing and chain rule. Okay, so that's my one slide introduction to information theory. Okay, so this is the theorem that motivated this line of work, which is by Xu and Draginsky in 2017. So under some assumptions on the loss function, so assuming that a loss function is what is called R sub Gaussian for every w. So this function L of w comma x, if you fix a little w, this is now a random variable in x. I mean, this is a random variable that is defined using that x, which is your data basically, or a single point of your data set. And what under the assumption that LWX is sub Gaussian for every single choice of w, the result is that you can bound generalization error using by the term on the right, which is the square root of mutual information divided by n. So I just want to point out two things, that so mutual information, as I said, it's some way of quantifying how much information there is between S and W, right? So this is how much information does the data set S contain about the output W, or how much information does W contain about S. When I started the talk, I said that there is some relation between this information, because if the curve W contains more information, then it seems that it is overfitting. If it contains less information, then it's probably not overfitting. So this is doing the second part of it. So it's saying that if the curve contains less information about S, if you have obtained the curve using limited information about the data set, then you are guaranteed to not overfit, right? So this generalization error is guaranteed to be small. But you can also make this, so you can make mutual information 0 by choosing your W to be completely independent of S. So if you look at your data set and you generate a W independently without even looking at your data set, that W is going to be independent of S. Mutual information will be 0, generalization error will be 0, which is good, right? Not really. So the way we have defined generalization error is, it's the difference between how an algorithm performs the test set and the train set, but it doesn't mean that it has to perform well on the test set and the train set. So if you have an algorithm that performs really badly on the test set and really badly on the train set, it could still have 0 generalization error. and that's fine as far as this result is concerned. So just this is just to point out that really what we care about is the generalization error plus this other term as well, and you want the sum of these two to be small. But right now I'm only focusing on one of them because the other one has its own analysis. So if you can bound this generalization error, use some other analysis for the second term, then the sum is what you would really care about. Okay, right. So this is the result that started this line of work, and so we were just curious about how one would go about using this to get actual bounds on optimization algorithms that people use in actual algorithms, right? So the idea is that this W that we have generated using the data set S did not come from thin air. Like there was some procedure that you followed, you used the data set S in some nice way, and then you arrived at this final output W. And often the procedure that we might have followed is some kind of an iterative update rule. Right? So you start with some initial estimate W0. Say, think of stochastic gradient descent. You start with W0, you pick some point from your data set, figure out a direction, figure out the gradient at that point, move there. And then you get a new iterate W1, then pick some other point, follow the gradient that it gives, arrive at a W2, do it for a long time, and then eventually just output the final guy WT, or sometimes you also output the average of everything that you have seen so far. Doesn't really change the result, but that's essentially how one would reach at that final output W. You don't start from a data set and immediately get a W. You often follow some kind of an iterative procedure, and then you land up at W. Right? And this earlier result said that this generalization error can be bounded using the information between your data set S and the final guy at W. So if you want to get some kind of a bound on the information between your data set S and the W, maybe the way to go about that is to look at the information at each step along this iteration. So if you can show that the overall information is somehow bounded by the information in each step, then you can get some kind of a bound which says that the overall information is small because the information at each step is small, and that's why the I of W comma S is also going to be small. So that's a rough idea. Yeah.
Sir, the way you define test error, you needed distribution, underlying distribution of your input, right?
Yes, the true distribution of the input. Yes.
Do we have that distribution?
No, we don't have that. Yeah.
How did you get a bound?
So I'm not bounding the test error right now. I'm bounding the test error minus the train error, which is also, you're right that the test error minus the train error has a joint distribution and a product distribution showing up, but I'm not actually calculating the test error and train error. I'm just saying that this bound holds for the, I don't have to calculate the test error to write the bound. Right, the bound depends on mutual information. So it's saying that if you were somehow able to calculate mutual information, then you would be able to calculate this bound. So this question is still kind of up in the air, how do you calculate this mutual information? Which is where this idea comes in, that one way to calculate mutual information is to notice that if you have an iterative algorithm, then it might be easier to calculate mutual information if you were able to calculate it at each step. Let's see. Okay. Right. So this is the class of algorithms that we ended up considering. So class of algorithms. So the canonical example is what is called stochastic gradient Langevin dynamics, which means you start at a point, you take a step in the direction of the gradient. So you're trying to minimize this loss function, right? You start at some initial estimate, take a step in the direction of the gradient, and then deliberately take a completely random step, like add Gaussian noise basically to where you were. Okay, so move in the direction of the gradient, add some noise. Now you land up at some new kind of a random point, which is close to where you landed up when you took your first step. Then you again calculate the gradient, move in that direction, then deliberately take a random step and move somewhere else. STLD, the stochastic gradient Langevin dynamics, is used in order to sample points from a distribution that you are interested in. Okay, so that's where it is primarily used. But sampling is related to optimization, because if you have a function and you are sampling from that function, you are going to get samples from the point where the PDF is maximized more often than you get samples from other points. So if you want to maximize a function, you might as well say that I want to generate samples from some density which is related to the function in some inverse way, like e to the minus phi or something. Okay. So that's where one place where SGLD comes into optimization. Another place where SGLD kind of comes is when you are trying to optimize a function and you want to escape from saddle points. So suppose you escape from local minima. Suppose you are minimizing a function and you accidentally land up in a local minima. One thing you could do is to just take a random step and hope that you get out of it. If you minimize a function, you land up at a local minima, just take a random jump and hope that you are now outside of it and then start minimizing it again. Okay, so there are some motivations for why one would consider taking such a random step after every gradient step. Okay. The motivation for us is that if you take a gradient step, you are clearly using the data to take that gradient step. But that additional random noise step is completely independent of your data set. Right? So that's where you are kind of controlling the information. You are deliberately destroying some information so that the overall information between W, the last point that you land up at, and your entire data set is small. So if you were to deliberately destroy information at each step, then you kind of ensure that the total information between S and W is not going to be very big. So that's the rough idea. I will just focus on this particular expression, that what we are doing here is the next iterate is obtained from the previous iterate by moving in the direction of the gradient. So this F is, just think of it as the gradient, and then add some noise. Okay. So that's all that we are doing, and then we are going to run this kind of iterative algorithm for t time steps, and then output some function F of everything that you have seen so far.
So noise is decreasing over time?
The noise is
variance, yeah.
Yes. So right now I am not saying anything. It could be increasing, it could be decreasing. So when you actually have an algorithm like SGLD, then we are going to plug in the parameters of the noise that are used in that algorithm and calculate what do our bounds look like for that class. So I mean, you don't want the noise to be too large, because then you're not effectively minimizing the training error. At the same time, you don't want it to be too small, because you want to make sure that your mutual information is low. So there is some sweet spot where so your final bound is the sum of two terms. It's the training error and the generalization error. So you try to pick a noise which is balancing both these terms, and the bound is as the smallest possible bound. Yeah. Okay, so we have a bunch of assumptions. The only assumption that is worth really thinking about is the final one, which is that the sampling is done without looking at the W's. So all that we are trying to say here is that let's say you are using stochastic gradient descent. In stochastic gradient descent, you have a data set, you randomly pick a point, then that point gives you some direction of gradient, and then you move there. So all that this last condition is saying is that the way you choose the next point to sample does not depend on how the algorithm has proceeded so far. So it's some pre-decided strategy that you have already decided you are going to uniformly, you're going to choose points uniformly at random, or you are going to cycle through the points in some way, or anything. But you are not allowed to say that, well, this algorithm is proceeding in this particular manner, and I now want it to move there, so I'm going to deliberately pick this point to make it move there. So that's something that you are not allowed to do. Yeah.
So suppose you stop after k steps.
Mm-hmm.
Suppose, then isn't it same as starting from W0 plus xi I plus? So in a way you just change your initial point.
No, because it's really difficult to predict where you will land up in t steps, right? So because you're also taking the gradient, and you're not just adding noise. You're taking the gradient at that point, then you add noise. Then you land up at this noisy point, then you take a gradient at a noisy point and add noise again. Yeah. So you can't invert it easily. Like, yes?
Sorry, I might have missed what is ZT here?
So ZT, it's sort of, it's like resampling of your data set. So the original data set is x1, x2, xn.
Yes.
But you're allowed to resample the data set as many times as you want. So the idea being that you cycle through your data multiple times and then eventually kind of stop. So Z is the resampled version. So at time t, you sample some mini batch from your data set, and ZT is that mini batch. The sample size is kind of dependent on the algorithm. Like it could be the entire data set, which means you're taking an actual gradient. It could just be one single point. It depends on the algorithm. Yeah, we don't have any restriction on how big or small it has to be. Yeah. Okay. All right. So that's the only assumption worth talking about. The last assumption. And our main result is the following, that if you have this kind of an algorithm and this kind of a sampling strategy, then you can bound the mutual information between your data set S and the final point W that you will end up at in this particular fashion. So eta t and sigma t recall the step sizes and the amount of noise that you are adding. One to note from this bound is that this bound is getting worse with t, which means that the longer you are optimizing, the worse your bound gets. The intuition is that well, the longer you optimize, the more you are minimizing your training error. So you might be overfitting. Basically, longer you optimize, the more the chances of overfitting. So that's roughly what this bound is trying to say, that it's some bound that depends on how much noise you add and also depends on how long you run the algorithm. Okay. And there are some implications. So once you have this bound, you can basically plug this bound into existing results, which say that once you have a mutual information bound, of course you can use the Shu and Draginsky results to say that what is the generalization error bounds that you get. So both this top result and the bottom result are just obtained by taking this information bound and plugging into the result. So just to show that they can be useful, nothing super deep going on in these 2 points. All right. So as I said, like the canonical example that we had in mind was the stochastic gradient Langevin dynamics. You take a gradient step and deliberately add Gaussian noise. So we plugged in what are the standard parameters that people use in SGLT. So for example, the sigma t square, the amount of noise, is equal to the step size eta t. So you can, if you plug in these kinds of bounds, then you get a generalization error that is increasing like square root log t over root n. So it is increasing, but it doesn't have to increase, say, linearly. Even though the sum is with t terms, it doesn't have to increase linearly. Also, there is a square root n below, so depending on the relation between n and t, it could actually be small. Right. I should comment that the best known bounds for the stochastic gradient Langevin dynamics are actually order 1 over n. So our bounds are 1 over root n, which are not optimal, but there is something to be gained by using the information. So this is one kind of one side effect of using information theoretic approach. You get bounds that are extremely general. For example, these bounds hold for your final output W can be any function of your iterates. We don't really care what it looks like. But in improving these very general results, you often lose the tightness of the results. So here, the result by Mo et al. Is kind of for a specific formulation of the SGLT, and you can show stronger results for such specific formulations. So this is kind of a theme, or this is something that I have been observing, that information theory is very useful for getting bounds, but you may not always get tight bounds. Yes.
Yeah. Sorry, please ask me. What is n and t? Why it is? Yeah.
So t is time. So t is how long you want to run the optimization procedure, and n is the size of your data set. So for example, n can be 100, which means you have only 100 points.
Are you talking size of S?
Yes, that's n is the size of S. Yeah, and t is how long you want to run the procedure.
Training data set.
The training data set, yes. Yeah. Yeah, question?
Can I use a similar reasoning, like by setting sigma to 0, can I argue for SGD too similarly?
I'll come to that in a bit. Yeah, it's a good question. All right. I will skip these, but there are some other noisy algorithms that you can apply this method to as well. And the proof, as I said, really uses only 2 facts. We are only going to use chain rule of mutual information and data processing. And it turns out that this particular problem has a lot of Markov chains because of this iterative nature. The next point that you'll end up at depends on what point you just, or what mini batch you just sampled, and where you are sitting right now, and also that random Gaussian noise. So you can write a very long, nice Markov chain, and essentially write the mutual information between the entire sequences of the W's and the entire sequences of your mini batches as some chain rule formulation, which is actually easy to parse. So on the right hand side, it's just saying conditioned on WT minus 1. So given that you're sitting at WT minus 1, this is the information between ZT, which is the mini batch that you sampled, and WT, the place where you landed up at. Okay, so this is exactly this one step kind of an argument. So if you can make each of these T terms small, then of course you're going to make this small, and this happens to be a bound on, upper bound on the ISW. So the mutual information that we care about, IWS, it's sitting somewhere here, so that is less equal this, and that is exactly equal to that. So if you can control this sum, then you're kind of good. And the way to control this sum is using essentially some maximum entropy properties of the Gaussians. Okay, so I guess that's one more property that I need, that for a fixed variance Gaussian has the maximum entropy. Okay, so that kind of gives this one step bound, that the mutual information in one step is upper bounded by this, and then I just take a sum over all possible steps and get the overall bound. So that's kind of a one line proof sketch, or one slide proof sketch. And okay, this is where your question comes in, that what is, so these are all the criticisms that I have about using mutual information kind of bounds to get generalization error bounds. So one thing is that there are many cases in which mutual information is just infinite. Right? And if mutual information is infinite, we are in trouble, because you have generalization error upper bounded by IWS, and that is infinite, so you basically have a useless bound. Okay, and what are some examples of cases where you get infinite mutual information, where every time you have some deterministic operation going on? For example, when you have linear regression, the W is a function of X of the data set S. Whenever you have deterministic functions, mutual information is not well behaved, it just shoots up to infinity. Okay, so if you directly try to plug in these bounds, you are going to get useless bounds. And also you can use a similar argument and say that even for stochastic gradient descent, where you are not adding any noise, you run into the same issue, because even though it's not deterministic, there are still only countably many points that you would land up at, and that countably many points creates some atomic kind of atoms in the distribution, and that gives you infinite mutual information. The point of this argument is that we would like to use mutual information, but there are many very simple, not very pathological cases where mutual information just becomes infinite and we cannot use this bound. So the reason why you're taking SGLD kind of algorithms where you're adding noise, it's actually essential for this bound to even work, because if you're not adding noise, then you get infinite mutual information and you're kind of in trouble. So, so that's why we decided to use something other than mutual information. So I'll just explain what these bounds are in terms of. So there is this concept called Wasserstein metric. So think about whenever you are given two distributions, there are various ways you can measure the distance between these two distributions. The simplest way is say something like total variation, where you just take the integral of absolute value of p of x minus q of x and divide by 2. And this is kind of a more complicated way, but it is basically a way to measure distance between two densities. So here are two distributions. So you have one distribution mu and another distribution nu. The Wasserstein metric says that it's kind of like you want to transport this kind of, imagine there is a pile of mud here, and you want to move this pile of mud to another pile of mud on the other side. But every time you move a chunk of mud, you pay some cost, because it takes some effort to move this piece of mud from a location here to some other location there. And you want to minimize the cost. So you want to minimize the amount of effort that it takes for you to move that mu to that nu. And if you were to try to calculate what is the minimum amount of effort that I need to expend in moving mu from nu, that gives you some number, and that number happens to be a metric. So it happens to be a notion of distance between mu and nu, as long as your cost is some nice cost. Okay. Okay, so this is some way of defining distance between distributions, and so it's not really, so I guess where it diverges from mutual information is that in mutual information we have KL divergence. KL divergence is some notion of separation, but really it's not a metric. This is a metric and it's a right notion of separation. So in that sense, it has some additional properties over KL divergence, but it also lacks some other properties that will become evident in a bit. So if I were to use these Wasserstein distance based bounds, then I don't need sub-Gaussianity assumptions anymore. The only assumption is some assumption which says that the loss function is Lipschitz. Okay, so under this loss function, what I ended up showing with ATN is that you can upper bound this generalization error by this term on the right hand side. So let me just parse what this is trying to say. So P of S is your data distribution, this IID, n IID samples x1, x2, xn. P of S given W is, if I tell you that after running the algorithm you landed at W and you want to guess the points starting from that W, then what is the distribution of these n points from that W? So P of S given W is kind of the distribution of the points from that one, given that you landed up at W, and then you are integrating it over the marginal of W. So if you think of it, this is kind of like a variance in the space of distribution. So note that the average of P of S given W, according to this P of W, is P of S. So think of P of S as sitting at the center and P of S given W as being points sort of all around it. And this is measuring the distance between P of S and P of S given W, and taking kind of the square of the error. If P is equal to 2, it's taking the square of the distance and taking a square root. So in some sense, it is like the variance in the space of distributions, and it is measuring how far away, how much information, it's roughly measuring how much information the W contains about the S. So for example, if W is completely independent of S, then this P of S given W is just P of S, because knowing W does not affect S at all. So this whole thing is just 0. So at least it matches, the generalization error is actually 0 when W is independent of S. Yes, but so right now I'll just leave this bound as is, just saying that it is some notion of separation in the space of distribution, some notion of variance in the space of distributions. Okay. So comparing the two bounds, so fine, we have this Wasserstein bound and we have an information theoretic bound. We do know that in some cases the information theoretic bound is infinite, and in those cases the Wasserstein bound is not infinite. So at least in those cases we are kind of good. But is there a direct way to compare these two bounds? And it turns out that that is not really the case. You can't always compare the two bounds, but in some really sanitized nice cases you can compare those bounds. So these nice cases are when your random variable x, which is the data distribution, is a Gaussian distribution. So if you have n IID points which are Gaussian, then there are some inequalities called transportation inequalities, which allow you to basically bound Wasserstein distance using KL divergence. I won't go into details, but sometimes for Gaussian distributions in particular, there are these or log concave distributions. You can say that transportation inequalities exist, and you plug in the transportation inequality and you get this kind of a bound. So the left hand side is precisely the Wasserstein bound that we had earlier, and the right hand side is essentially the same as the square root mutual information over n bound that we had, that Shu and Draginsky had. So at least this result is saying that you can't always compare it, but here's at least one example where these bounds are better, and this bound is not shooting up to infinity in the cases where mutual information is shooting up to infinity. Of course, the issue is how do you calculate this bound? So the benefit of using mutual information was chain rule, data processing, all these nice properties. Wasserstein distance is a metric, but it doesn't have chain rule, data processing, all these nice properties. So even if you have an iterative algorithm, how do you actually calculate the left hand side and compare it to the right hand side is still sort of unsolved. Okay. So I will skip the proof sketch and directly jump to some speculations and open problems. So one is that this idea of stability that I said earlier is kind of related to this forward channel. So when you have, it is asking the question, if you change your input a little bit, how much does the output change? Whereas our bounds for the generalization error are somehow in terms of the reverse channel. So it's saying if you want to solve this reverse problem of guessing the points from the curve, how kind of stable is the reverse channel, and that gives you generalization error bounds. It just so happens that mutual information is symmetric. So forward channel, reverse channel, it doesn't really care, IWS is the same. But these Wasserstein bounds do actually change whether when you're looking at forward and reverse. So I guess one just idea would be, let's say you want to actually minimize the Wasserstein bound. Is there any way you could make the backward channel more noisy, or do some kind of a geometric transformation of the backward channel to make sure the Wasserstein bound is small? Not that it, so we are just making the bound small. So what I'm trying to say is there might be ways to make it generalize well without making the Wasserstein bound small as well. But one way to ensure that it is generalizing well is to deliberately make some modifications to the backward channel, which I'm not sure what to do there. And the second is, this is very closely connected to an area of information theory called rate distortion theory. So roughly what happens in this area is you're trying to optimally represent some information, but you're trying to minimize the expected distortion. You're trying to compress information, but also compress that it is distorted in the least possible, or distorted by the least possible measure, by some measure d. And this problem has a nice kind of formulation that you're trying to minimize distortion. So you're taking x and compressing it into y, and you want to minimize distortion subject to some mutual information condition. And if you look at it, this looks very similar to the problem that we have. So what we are trying to do is the same. So py given x is your algorithm. You're trying to minimize the expected loss subject to some bound on mutual information. This bound on mutual information is saying that you want it to generalize well as well. So while keeping mutual information small, you want to compress it. So it's very similar to rate distortion theory. Some differences are in the assumptions on the loss function basically. So the loss function is generally assumed to be separable. In information theory here, that separability assumption doesn't hold. One idea that was suggested to me a while ago was to try and use single shot compression results from information theory so that you don't need the separability assumption. I haven't yet explored them, but I'm planning to look into them in the near future. And that's it. These are a couple of references. And thank you. Feel free to ask me any questions. Yeah.